Hey guys, in this video we're going to look at question A-5 from the 2005 Putnam math competition. We have a question that just has one word. It says evaluate, and then we see this definite integral from 0 to 1 of the natural logarithm of x plus 1 over x squared plus 1 dx. Now, we notice in the denominator this x squared plus 1, and if you recall, the derivative, if we take the derivative with respect to x of the arctangent of x, then what that is equal to is 1 over x squared plus 1. And this 1 over x squared plus 1, we see this in our integral. In fact, that is being multiplied by the natural logarithm of x plus 1. So let's apply a u substitution, and we will say u equals the arctangent of x, which means that our du is going to equal dx over x squared plus 1. Now we're going to have to convert our bounds, so we say, okay, well, the upper bound is going to be u of 1, and this will equal the arctangent of 1. And the arctangent of 1 just says, okay, well, for what angle is tangent 1? Well, tangent is 1 when sine equals cosine, because tangent is the ratio of sine over cosine. And sine equals cosine at pi over 4, if you recall from the unit circle. So this will equal pi over 4. And likewise for our other bound, our lower bound, we have u of 0 equals the arctangent of 0. And this basically asks the question, okay, well, for what angle is tangent 0? Well, that'll be where sine is equal to 0, because tangent is equal to sine over cosine. And sine equals 0 when our theta is 0. So our new bounds will be from 0 to pi over 4. So let's rewrite this integral. And now we have the integral from 0 to pi over 4 of ln of, well, what is our x? Up here, our u is equal to the arctangent of x, which means that our x is going to equal the tangent of u. It'll be the other way around. So this will be ln tangent of u plus 1. And notice the 1 over x squared plus 1 times the dx, that just equals du. So now we've converted our integral, and this honestly looks a lot more simple than the first one, but we're not quite in a position where we're able to evaluate it. So let's isolate the integrand, and I will write that here on the upper right hand corner. So we have tangent, or rather the natural logarithm of tangent of u plus 1. Now, one property of logarithms is if we have ln of a over b, then this is equal to ln of a minus ln of b. So let's see if we can somehow change this or convert this tangent of u plus 1 into a fraction. That way we can then separate this natural logarithm into two natural logarithms that are, where one is being subtracted from the other. Now, the way we can do that is we can say, okay, well, tangent is just sine of u over cosine of u. And our 1, well, if we want a similar denominator, then we can say, okay, well, this will be cosine of u over cosine of u. And now we can add these together, and we say, okay, well, now we have ln of, that's sine of u, and then plus cosine of u over cosine of u. And now we can apply this property from above, and we have the natural logarithm of sine of u plus cosine of u, and this is equal to, or rather minus ln of cosine of u. And so these two are equal. Well, we notice on the natural logarithm on the left, inside we have sine of u plus cosine of u. So let's play around with some trig identities or properties and see if we can replace that with something that is explicitly in terms of cosine, because the logarithm on the right hand side, that is explicitly in terms of cosine. So the property that we're going to use, and I will write it down here, it is cosine of some value or some angle, let's say alpha, minus cosine of beta is equal to cosine of alpha times cosine beta plus sine alpha sine beta. And this is a trigonometric property. So we notice that we have sine of u plus cosine of u. And here we have a cosine of beta and a sine of beta. So if we choose our alpha, if we say alpha equals pi over 4, then what we will get is we will say, okay, well, cosine of pi over 4 minus beta, this is equal to, and we're choosing pi over 4 here because if you see, we want to isolate this cosine beta and sine beta. So we need a value for which cosine and sine, these two, are going to be equal. That way we can divide by the same value, and then we'll isolate the cosine beta plus sine beta. So then we'll get cosine of pi over 4, and that's going to be root 2 over 2. So root 2 over 2, cosine beta, and this will be plus, and that'll be root 2 over 2 sine beta. And now if we solve for cosine beta plus sine beta, well, we'll multiply both sides by 2 over root 2. So then we'll get, well, this will be 2 over the square root of 2 cosine pi over 4 minus beta. This is equal to cosine, and I'll just write it the other way around that we have it written up there. So sine beta plus cosine beta. Now, just a matter of simplification, notice here that 2 over root 2, well, if we multiply the numerator and the denominator by root 2, then we will just get 2 root 2 over 2, and this is equal to root 2. So I will just rewrite that right here. Well, cool. What we've done now is we've sort of derived another property from a property that we already had in order to replace this sine u plus cosine of u with something that is written explicitly in terms of cosine. So now we will rewrite that. Okay, so we have, this is the natural logarithm of root 2 and then cosine of pi over 4, and now this isn't minus beta but rather minus u, and then this is equal to or not equal, I've done that twice now, so now this is minus ln of cosine of u. So we have this root 2 being multiplied by the cosine of pi over 4 minus u, which means we can once again use a property of logarithms, and we can take that out and we can add it. So we can say, well, this is ln of root 2 plus ln of cosine of pi over 4 minus u, and then minus ln of cosine of u. Well, this, and we will once again apply another property of logarithms. Our ln, and I will write this up here, our ln of root 2, well, this is equal to ln of 2 to the 1/2. And whenever we're taking the natural logarithm or even the logarithm of a number that's being raised to an exponent, we can take that exponent and we can bring it out front. So this is equal to 1/2 ln of 2, so ln 2, plus ln of cosine of pi over 4 minus u, and then minus ln of cosine of u. So if we look back to our integral, and that's right here, we're taking this integral from 0 to pi over 4. And if we just focus on the integral of these last two terms, then we'll notice something interesting, because we see that we're taking it from 0 to pi over 4, and we notice this pi over 4 minus u inside of this cosine. So what happens if we try to take the integral? Well, what we'll do is we'll say, okay, well, I'm just going to try to take the integral first from 0 to pi over 4 of ln of cosine of pi over 4 minus u du. Well, I'm going to get rid of this pi over 4 minus u, and I'll do a v substitution, and I will say that my v is equal to pi over 4 minus u, which means my dv would equal minus du. And now I want to solve for my du, so my du is equal to minus dv. Now solving for our bounds, well, v of pi over 4 will equal, well, that'll be pi over 4 minus pi over 4, so that equals 0. And then we'll have v of 0, and this will equal pi over 4 minus 0, which is pi over 4. So now if we rewrite this integral, then we will have the integral from pi over 4 to 0, and then we will bring our negative out front. Now this will be ln of cosine of v dv. Now if we get rid of this negative, we can flip our bounds, so this equals the integral from 0 to pi over 4 of the natural logarithm of cosine of v dv. Well, wonderful. Now that we've written this more complicated integral in terms of something easier, let's integrate this entire thing. Let's integrate this entire thing and see what happens. So we use green now. So we have the integral of 0 to pi over 4, and then this is of 1/2 ln 2. And then this is with respect to u, so then du. And then this will be plus the integral from 0 to pi over 4. And now this is ln of cosine, and this is v because we had a v right there, so dv. And then we'll have a minus the integral from 0 to pi over 4 of ln of cosine of u du. Now, although the integral on the far right is written in terms of u and the integral in the middle is written in terms of v, they're 100% identical, so they'll actually equal each other, and we can cancel them out. So let's cancel those two out. And now what we have is we just have the integral from 0 to pi over 4 of 1/2 ln 2. So now we can, switching back, so now if we evaluate the integral of this, then that would be 1/2 ln 2 times x, and then evaluated from 0 to pi over 4. And obviously when we plug in 0, that'll just be 0, so then we'll just evaluate it from pi over 4, and then this will be, well, pi over 8 ln 2. And this is a pretty fascinating integral because it ends up being a lot simpler than one would expect, and that tends to be the trend with these Putnam questions. Another way to intuitively think about what we did, this cosine of pi over 4 minus u is really just a shift of our cosine of u. Notice that, when we plug in pi over 4 into cosine, then we get cosine of pi over 4. But when we plug in pi over 4 into cosine of pi over 4 minus u, well, then we get cosine of 0. So basically what this has done is it's just shifted the graph of cosine pi over 4 units to the left. And when we take the integral of that, well, what it ends up doing is it also sort of shifts the bounds over 4 units to the left. So we're shifting the graph, but we're also shifting the bounds with it. And that's why these two cancel out. Well, I hope you enjoyed the video. I hope you found it helpful. I will be posting more Putnam questions in the future, so look forward to those. If you have any questions, please leave a comment below. I'll be sure to get to them soon, and I'll see you in the next video.